Good morning, good afternoon, good evening, depending on the time that you've opened this lecture PowerPoint. So, as I did promise you yesterday, today we're supposed to look at the cardiovascular physiology, but I must make mention that the cardiovascular physiology, it is very broad because you need to pick it up from the scratch, understanding the basics for the cardiovascular physiology. So MBCHB 3.1, your limit is you are not going into detail by looking at the structure of the blood vessels and the stuff, because basic about the cardiac physiology, we're just basically playing around with the blood vessels, the histology and the physiology of the blood vessels, such as the arteries, the veins, and the capillaries. But we are not going deep into that. You do that in your 3.2 when you start dealing with the histology of the CVS. So basically for today, the area of concentration where I see you guys are behind is on the cardiac output, the cardiac cycle, and some of the factors that can attribute to having high cardiac output or low cardiac output. So in this lecture PowerPoint, we'll basically go into detail by understanding what is cardiac output. So understanding what a cardiac output is, you must have a very good knowledge about your anatomy of the heart, about the physiology of the heart, those basic things and basic stuffs about the heart, its anatomy and its physiology. You need to be able to record that information, because cardiac output, its explanation will be totally based on the anatomy and the physiology of the heart. Aside from that, cardiac output is full of calculations, dealing with numbers. So you shouldn't throw away or forget totally your basic mathematics foundation, the laws of multiplication and addition. So those basic mathematics foundation, will be applying them as we'll be dealing with the cardiac output, because cardiac output is just basically to do with the normal range for the cardiac output, and how do you know to say that's a normal range. Okay, so basically to simplify it for you, under the cardiac physiology, I've excluded a lot of stuffs and they just focused on the cardiac output. So you must get me right. Cardiac physiology, it is not only centered at cardiac output. You must be able to know some of the minor things that attributes to making the whole of the cardiovascular physiology, because in your MCQs, some of the questions can be gotten from some of the parts or some of the topics of the cardiac physiology that we've excluded. So in this PowerPoint, I'm assuming that those basic steps for the cardiovascular physiology, you have a bit of a know-how or a little of a know-how about them. So this is just basically to assist you with the cardiac output and the regulation of the cardiac output. So basically about the cardiac output, so let me use my pen here and say, so our area of concentration for today in this PowerPoint, it is to be able to understand what cardiac output is, but we will not just go straight into understanding what cardiac output is. I will write the general formula, and from that general formula, we'll start extracting each part and going into details into each part. So our formula under the cardiovascular physiology that we must all be familiar with. It is the formula for calculating the blood pressure. So what's the formula for calculating the blood pressure? It's blood pressure is equal to cardiac output times the total peripheral resistance. So this is the formula that will be playing around throughout this lecture video, through this lecture PowerPoint. Blood pressure is equal to cardiac output times the total peripheral resistance. So to make it very easier for you, blood pressure, the formula for blood pressure is this one, but we'll talk about the blood pressure at last. So what we are going to do first is, let's first deal with what is this cardiac output and what is this total peripheral resistance. So we'll start with the cardiac output. So you shouldn't throw this formula away because you'll be referring to it. Blood pressure is equal to cardiac output. So cardiac output is abbreviated as CO. That is cardiac output. Capital letter C and the capital letter O. If you write capital letter C with a small letter O, that is now the carbon monoxide. So you must be very, very accurate as you are doing your calculations basically on the cardiac output. So capital letter C and capital letter O. You write capital letter C, small letter O, that is now you are referring to something else, which is carbon monoxide. So be very accurate on that. So having known this formula, we are going to extract and look into details about the cardiac output, what it is. All right, so cardiac output, what it is. So cardiac output, by definition, as you can see on the screen here, it is just the volume which is being pumped by the left ventricles each minute. So to summarize this definition for the cardiac output, so here we've just specified as the amount of, or the amount or the volume of blood that is being pumped out by the ventricles. If you are to be if you're about to tackle both the right and the left, you just say it is amount of blood that is pumped by the ventricles. If you are to be specific, by the left ventricles, because we are just concerned with the amount of the volume of blood rather that is being pumped by the left ventricles, and we know the anatomy of the left ventricles and what kind of blood they carry. So from the general anatomy of your heart, you have the chambers, the right and the left chamber. You have the two atriums. In short, physiologically you have about anatomically you have 4 chambers. Physiologically you have 2 chambers. So 2 chambers, that is the right and the left chamber. That is physiologically. Anatomically you have the left atrium, the left ventricle, the right atrium, the right ventricle. So by this time we must be able to differentiate what kind of blood do the right atrium and the right ventricle carry, and what kind of blood is found in the left atrium and the left ventricle. And of which, not to say, in the left ventricles, this are going to receive the oxygenated blood that will be pumped through the aorta and to all parts of the body. For the right side of the heart, is receiving it's receiving the deoxygenated blood that will be sent through the pulmonary, going to the lungs for the oxygenation. So that basically imagination about the heart, you should have it at the back of your mind. So when you're talking of cardiac output, you're just referring to the volume of blood that is being pumped by the left ventricles each minute. And you must be able to understand to say when blood is leaving the left ventricles, where does it go? It is being pumped into the aorta and finally to the all part of the body. So now let me give you the formula for calculating the cardiac output. Having understood what the cardiac output is, you must be able to know what is the formula for the cardiac output. So cardiac output is equal to the heart rate times the stroke volume. Now again, you see this will be a very, very long lecture. Having done what the formula for the cardiac output is, which is equal to the heart rate times the stroke volume, we'll need again to go into details by looking at what are some of the factors that can affect the heart rate, and what are some of the factors that can affect the stroke volume, and what is this stroke volume. So from the basic understanding is that once you have the heart rate which is high, this will result into having a high cardiac output. And if the stroke volume is very high, it will result into having high cardiac output, and the opposite is true. The lower the heart rate, the lower the cardiac output. The lower the stroke volume, the lower it will result into the cardiac output. So now, on the heart rate, we will need to go into details by looking what is the heart rate, what is the normal range for the heart rate, and what is the stroke volume, and what is the normal range for the stroke volume. So we'll begin with the heart rate, then we'll go to the stroke volume. So this is the formula for the cardiac output. Cardiac output is equal to heart rate times the stroke volume. Now, what is the normal value for the heart rate? So heart rate, the normal value, it is about so in order to cut all the angles, because when you're using different literatures, they will give you different kind of ranges here. But the normal heart rate, if you're about to cover all, it is about 60 to 100 beats per minute. So this is the normal heart rate. So where is this normal heart rate coming from? The normal heart rate is part of the cardiac output formula. Cardiac output is equal to heart rate times your stroke volume. So now, let's go deep and understand what are some of the things that can affect the heart rate. So now, the factors that can affect the heart rate in either a person having if a person, what are some of the factors that can result into the heart rate being high, and what are some of the factors that can result into having or contribute to a lower heart rate. So now let's begin with it, the positive factors that can contribute to heart rate being high. So some of these positive factors include, the major one, it is from your sympathetic nervous system. Yesterday we did we learned about the autonomic nervous system. We went into details by understanding what is the divisions of the autonomic nervous system. We did learn into details what is the sympathetic nervous system and what is the parasympathetic nervous system. So both of these, the sympathetic and the parasympathetic nervous system, they are going to cause an effect on the heart rate in either stimulating the heart rate, meaning to say it will result into high heart rate, or resulting into a lower heart rate. So now for the positive factors that are going to cause the heart rate to be high, the major ones include your sympathetic nervous system. So now, how does the sympathetic nervous system contribute to having a high heart rate? Remember that your myocardium, rather, or the cardiac muscles, they have certain receptors, and the kinds of receptors they have, those are what you call as the beta receptors. So these beta receptors from the sympathetic nervous system, if you remember very well, the sympathetic nervous system had the two types of neurons, the preganglionic and the postganglionic. At the autonomic ganglion, what type of neurotransmitters was being released? That was the cholinergic type of transmission, meaning to say we are releasing our acetylcholine. And at the peripheral synapse, we are releasing the adrenergic, meaning to say we are releasing the epinephrine and the norepinephrine. Now, I must make mention to say these two, the epinephrine and the norepinephrine, these ones are going to attach on the beta-1 receptors of these cardiac muscles. When they attach on the beta-1 receptors of the cardiac muscles, these ones will result into opening the calcium channels. And when the calcium channels are open, meaning to say the cell the cells are going to become depolarized, and they are going to generate action potential. When they generate action potential, this will result into the what? Into high heart rate. So that is a positive attribution of the sympathetic nervous system. It is as a result of the adrenergic neurotransmission, meaning to say we are releasing the norepinephrine that will attach on the beta-1 receptors of the myocardium. So specifically just dealing with the heart. Okay, and as a result of that, it will result into calcium influx, making the inside of the cell to be more depolarized, generating action potential, and resulting into the heart rate being high. So that is one of the positive factors. The other positive factor that can increase into high heart rate include the drugs. So drugs as well can cause the heart rate to be high. Okay, so basically there are a lot of factors that can contribute to a person having this high heart rate. So we are not going to mention all of them. We'll just mention the major ones. All right. So I hope we are moving at the same phase. Okay. So the other things that is going to attribute to a person having the high heart rate, this one though is not the major one. It is just the minor one, the body temperature. So the body temperature as well can result into a high heart rate, because the body temperature will result into the generation of the most of the metabolic activities that will result into the generating of energy in the form of ATP, and that will generally increase the heart rate. The third factor that will result into heart rate, they are the chemoreceptors. I must make mention again, these are the minor ones. The major one is the sympathetic nervous system, but also the chemoreceptors, they can result into high heart rate. Now, how do they result into the high heart rate for the chemoreceptors? First and foremost, from your anatomy, I believe you know where these chemoreceptors will be located. So some of the chemoreceptors will be located at the bifurcation point of the aorta, and some of them can be found on the arc of the aorta. And these chemoreceptors are only activated only in a situation where you have the partial oxygen the partial oxygen pressure is dropped or is low, and the partial carbon dioxide, the partial pressure for carbon dioxide is very high. So when there is this indifference between the two, where the the partial pressure for oxygen is very low and the partial pressure for carbon dioxide is very high. The other thing is the partial pressure, the pH will also be dropped. So as a result of the lower partial pressure for oxygen being low and the pH being low and the partial pressure for carbon dioxide being high, these ones will stimulate the chemoreceptors. And what will the chemoreceptors do? The chemoreceptors will send signals into the medulla oblongata. So in the medulla oblongata, they will communicate with a certain type of nucleus that is found in the medulla oblongata. And that is the nucleus that we call as the nucleus solitarius. So the nucleus solitarius in the medulla oblongata now will stimulate the sympathetic nervous system. And you know what the sympathetic nervous system, in terms of the neurotransmission, what they release? They release the norepinephrine and the epinephrine. I must make this differentiation that the function of the norepinephrine and epinephrine is totally different from what we know when we are dealing with the skeletal muscle physiology, basically under the neuromuscular junction. From the neuromuscular junction, when we are dealing with the excitable tissues, you understood to say we are releasing the acetylcholine in the synaptic cleft. And what will be the function of the acetylcholine? The acetylcholine will bind on those channels, allowing more sodium to flow into the postsynaptic and generating more of the action potential. But in the case of the autonomic nervous system, the acetylcholine will do the opposite of what it is doing in the skeletal muscle at the neuromuscular junction. So what did I say are the stimulatory factors for the heart rate? Number one, the sympathetic nervous system, because of the neurotransmission of the norepinephrine and the epinephrine that is binding on the beta-1 receptors. Number two, the body temperature, though this is the minor one. Number three, the chemoreceptors. The chemoreceptors are only activated when the partial pressure of oxygen is low and when the pH is very low, but the partial pressure for carbon dioxide is very high. As a result, these chemoreceptors will send signals to the medulla oblongata, to the nucleus solitarius, and the nucleus solitarius will respond by sending the impulses to activate the sympathetic nervous system, so that the sympathetic nervous system can release the norepinephrine and the epinephrine that will bind on the beta-1 receptors of these cardiac muscles, and as a result, it will result into the high heart rate, meaning to say the heart will be pumping very fast. So those are the factors that you need to know. I did make mention to say the normal heart rate, it is in the range of 60 to 100 beats per minute. So this is just the range that caters, that is just the normal range to cater in all the type of literature books that we're going to use, because other books or other textbook, they will refer to it as being in the range from 60 to 80. Other textbook, they refer to it from being 70 to 80. So the normal range is between 60 to 100 beats per minute. But again, I must make mention to say this is it is different. The heart rate is different depending with the gender. So the normal heart rate for the females and the normal heart rate for the males, it is totally different. And the normal heart rate for the fetus, it is also different. So to begin with, the fetal heart rate, it is not in the range of 60 to 100. The fetus has a very, very high heart rate, and it is in the range of 120 to 140 beats per minute. That is in the fetus. Don't mistake it. Don't mistake it with in an adult. So if a question is given, you have to pay much attention to the kinds of the individual you are dealing with in terms of age. If it is a fetus, not to say fetus, they have an exception. Their normal heart rate, it is 120 to 140 beats per minute. Okay, so I was just confirming if it was recording. Okay, where were we? Have forgotten. All right, on the fetal heart rate. So I was mentioning that the fetal heart rate, it is very high, slightly high. The normal range, it is 120 to 140 beats per minute, and in adults it is from 60 to 100 beats per minute. But males, they have a slightly lower heart rate as compared to the females. So that is the reason why, this other gender, they are always, I don't know how I can term it, but yeah, you understand. So the males, the normal heart rate for the males, it is about 64 to 72 beats per minute. And in females, it is from 72 to 80 beats per minute. Okay, so you need to put into consideration those variations, because a question can be given as 64 what year old comes to your facility with what. So you consider the gender of that person, and at the back of your mind you must know the normal heart rate in an adult with regards to the gender. And I must also make mention to say the heart rate, it keeps on increasing when the person is growing old. So in older clients, let me just say in older individuals, they have the higher heart rate. You don't expect them to have the lower heart rate. The more they grow older, the higher the heart rate it increases. Aside from that, there are these cardiovascular terms that we need to familiarize ourselves with regard to the heart rate. I know some of you have heard some of these terms: the bradycardia, the tachycardia. So what are these? So to start with, the bradycardia. Okay, hold on to that. What I'm just from mentioning, they are just the stimulatory factors that will increase the heart rate. I did not make mention about the factors that can lower the heart rate. So quickly, let me just give you the factors that can lower the heart rate. So one of the factors, it is the peripheral nervous system. Now you must be asking yourself, how is the the parasympathetic nervous system resulting into a dropped heart rate? The reason is very simple. Remember from the autonomic nervous system I did mention to say the parasympathetic nervous system, at the kind of the neurotransmission that is released at the autonomic ganglia and at the peripheral synapse, they are all both cholinergic. Meaning to say, if they are cholinergic, the kind of transmission, the kind of neurotransmitter they are releasing, it is the acetylcholine. And with an exception, I did mention to say in the autonomic nervous system, the acetylcholine, it does the vice versa from the skeletal muscle physiology that we learned on the excitable tissue. Under the excitable tissue, not to say this acetylcholine will result into, into action potential, generating action potential, depolarizing the cell, and so forth and so on. But in the case of the parasympathetic nervous system, let me just make mention what the acetylcholine will do when it is being released as the neurotransmitter. So when this acetylcholine, it is being released at the peripheral synapse as a neurotransmitter, what it will do, it is that number one, it will stimulate the potassium efflux. So you understand to say inside of these cells, we have the availability of potassium. And if this acetylcholine is going to stimulate the efflux of potassium, what basically happens is that the inside of the cell will become more negative. So now you might be asking yourself, why does the inside of the cell become negative? And you know to say when the inside of the cell become negative, it will become, let me just say, it will become more negative, meaning to say the inside of the cell will be hyperpolarized. Now, how does the inside of the cell become hyperpolarized? The inside of the cell become hyperpolarized as a result of the potassium efflux. So potassium efflux, that basically means to say the potassium ions that are inside of the cell, they are escaping the cell. That is the efflux. If at all ions are entering into the cell, that is the influx. So efflux, potassium is leaving the cell. So now you must understand to say the inside, when we have potassium inside of the cell, inside of that cell, this potassium, it can't exist on its own. It likes to bind to higher molecular proteins and to phosphates. And as this potassium leaves out the cell as a result of this acetylcholine, which was being released at the terminal peripheral synapse, this potassium will escape the cell, meaning to say it will leave the inside of the cell. Now, I must make mention to say, inside of the cell, it was attached to proteins and phosphates, and the proteins are highly negatively charged molecules. And that same applies to the phosphates. Phosphates are highly negatively charged molecules. So as potassium is escaping the cell, the highly proteins negative molecules that are attached to this potassium will detach. The reason being is that these proteins, they are very large molecules in such a manner that they can't exit through the channel that the potassium is using. They are very too large in such a manner that they can't escape the inside of the cell. And what do you think will happen? So potassium, yes, it is a positively charged. It is K with a positive 1 charge there. So now if it detaches from these proteins inside of the cell as it escapes, meaning to say these proteins inside of the cell will just remain freely on their own. And remember to say they are highly negative. So meaning to say the inside of the cell will become more negative than than they were before potassium detaches itself. So that is just basically the physiology behind it. So escape of the potassium will leave these highly negatively charged proteins and phosphates freely. And as a result of that, the inside of the cell will become more negative. When the inside of the cell become more negative, that is, we use the term hyperpolarization to refer to the high negativity of the cell. All right. So that was one factor that will result into the heart rate being low. So now, if the inside of the cell becomes highly negative, what does that tell you? It tells you to say you can't generate action potential, because we know to say the action potential, the voltage, it is about positive 30 millivolts. And since the inside of the cell is more negative, you are very far from obtaining the action potential. And that basically means to say you can't stimulate these the cardiac muscles to contract and cause that heartbeat for the contractility to occur. So that is just basically how the parasympathetic is going to do what to stimulate to lower the heart rate. Number two, it is high potassium. So high potassium is just basically what I'm just from explaining, how potassium is going to leave the cell and so forth and so on. All right. So having done that, also drugs, drugs can either stimulate the heart rate, or they can either do what? Lower the heart rate. So that is just basically one factor that you can add. So drugs can belong to both. They can either stimulate the heart rate, or they can either lower the heart rate. And at your level, you don't have to go into details in knowing which kind of drugs can increase the heart rate and which kind of drug can reduce the heart rate. Last one that can stimulate heart rate, it is calcium. So if you have too much calcium, which is the term that we call as the hypercalcemia, that can also increase the heart rate. All right. So now that was about the factors that stimulate the heart rate and the factors that can lower down, or that can lower the heart rate. So remember to say what I'm explaining here, it is just basically helping us to understand the cardiac output. Don't forget where we've started from. The whole main point is for us to understand the formula for the cardiac output, and now going into details by understanding the factors that can attribute to that component that makes up the full formula for the cardiac output. And what we've just explained here is just basically on the heart rate. So now there are two terms that I want you to distinguish, and these two terms are commonly used. One of them being the bradycardia, and the other one being the tachycardia. So these ones are basically very simple. I'll start with the bradycardia. So bradycardia, this is the physiological term, I don't know, or we can say the medical term that we use to refer to the heart rate that is below 60 beats per minute. Remember the normal heart rate, it is from 60 to 100. And if the heart rate it is below 60 beats per minute, we term that as bradycardia. And the opposite will be true for tachycardia. So tachycardia, this is the heart rate that is above 100 beats per minute. And of course, it has an exception depending with the age of the individual. Remember that the infants, they have 120 to 140 beats per minute. So if an infant comes to the facility with the mother and the heart rate, it's about 120. You can't call that as tachycardia, because in them, that is the normal heart rate. So you must be able to make those differentials. Having understood about the heart rate now, let's go to the next part that makes up the cardiac output, which is our stroke volume. So now, what is the stroke volume? You must be able to understand what is the stroke volume. So the stroke volume, by definition, this is just the volume which is in difference between the end diastolic volume and the end systolic volume. Now we are now dealing with the physiological terms. So these guys, they shouldn't even confuse you. When you say the stroke volume, we're just basically referring to the amount of volume that will remain after the end systolic volume, or after the end systolic contractility has taken place. So now we have two things. The formula for the stroke volume, it is the stroke volume. I will represent as SV. Stroke volume is equal to EdV minus ESV. This is the formula for the stroke volume. Sorry, that was stroke volume is equal to EdV minus the ESV. So what does this tell you? Stroke volume is equal to EdV stands for end diastolic volume, ESV stands for end systolic volume. So now SV, the normal systolic volume, it is about 70 beats per minute. It's about 70 beats per minute, but if you do the calculation of the units, it will cancel to remain as 70 mils per minute. And of course, we'll do some conversions here. But what I want you to know it is that this is the normal systolic volume, 70 mils per minute. So this is our stroke volume. Now, I need us to go deep and understanding what is this EdV and what is this ESV and what are the units. So I'll start with the EdV. So when you say EdV, the end diastolic volume, let me blow the chamber of the heart. So when we have the chamber, I'll just blow one, or let me just blow two for the simplicity purposes. So here I'll make a division. I have another chamber there, I have another chamber here. So let's assume to say these are the ventricles of the heart. So let me say I have blood there and I have blood there. So now this amount of blood that is here, you know where it is coming from. If this is my left side, this will be my right side. So this blood which has accumulated in the ventricles, both the right and the left ventricle, this is what we call as the end diastolic volume. So this end diastolic volume, it is a volume of blood that is available in the ventricles before the contraction of the ventricles. Because you know to say when contraction of ventricles has occurred, we'll push this blood, if it is in the left ventricle, push this blood through the aorta. If it is in the right ventricle, we'll push this blood through the pulmonary system. So now, before the contraction has occurred, this amount of blood that is in the ventricles, before the contraction has occurred to pump this blood out, it is what we are referring to as the EdV. And this amount of blood that is in the ventricles, it is measurable. So the normal EdV of blood that is in the ventricles before contraction has occurred, it is about 120. It is about 120 mils. So per every heartbeat, we are having this 120 mils. And let me just pair it with the end diastolic volume. So the end diastolic volume, this amount of blood that is going to remain after contraction has occurred. Now, I must make mention, when this 120 mils of blood that we have in the ventricles that we are referring to as the EdV, when contraction has occurred, this blood is going to be pumped out of the ventricles to the aorta and to the pulmonary. Now, not to say not all the blood is going to be pumped out in such a manner that in the ventricles are going to remain with zero. Some of the blood is going to remain in the ventricles. Not all blood, not all 120 mils which is in the ventricle is going to be pumped out. Some of the blood is going to remain in the ventricles. And that blood that is going to remain in the ventricles after the contraction has occurred, it is what we are referring to as the end systolic volume. The amount of blood that is remaining in the ventricles after the contraction has occurred. So those are two different things. End diastolic volume and end systolic volume. End diastolic volume, this is a volume of blood that is available in the ventricles before contraction has occurred. And the systolic volume, this amount of volume that remains in the ventricles after contraction has occurred. The normal value for the end systolic volume, it is about 50 to 70 mils. So meaning to say after contraction has occurred inside of these ventricles, the normal blood that should remain, it should be about 50 to 70 mils. So that is what we mean by end diastolic volume and and systolic volume. So now, having understood this, then our systolic, yes, our stroke volume therefore, okay, sorry, our stroke volume therefore is equal to EDV minus the ESV. So now, if we did mention to say EDV, it is about 120, that is the normal. So when you do 120 minus, so let's say maybe the ESV, it is about maybe 50. The difference that you are going to get, that will be the value for the stroke volume. So now at this point, you must be very sharp enough, because at some point the question can come, you've just been given the end diastolic volume, the end systolic volume, then you're asked to calculate for the to calculate for the cardiac output, and you'll be stuck to say no. And you've been given the heart rate. You've been given the heart rate, you've been given the end diastolic volume, you've been given the value for the end systolic volume, and you're being asked to calculate for the heart rate. Some of you can be stuck, you'll be like, no, we're not given for the stroke volume. So that is how you calculate for the stroke volume. So now, stroke volume, then what are the units? So let's generally deal with the units for the cardiac output, and we'll come back to that. So here there are examples that have been given. So I'm using the PowerPoint for Madame Lumboka. So here on the stroke volume, concentrate much here, we are given to say, I've just gone through what this is. Stroke volume is equal to EDV minus the ESV. So I did mention to say there's some variations. So it can either be in the range of 120 for the end diastolic. So it can be from 120 to 140 for the end diastolic. That is normal. And for the end systolic, it can either range from 50 to 70. So anywhere between, it is the normal range. So now in this case, I've been given to say our EDV is 135 mils. And by now, you know where this 135 mils is coming from. All right. Sorry for that. We'll do this. Okay. So by this time, you know what the EDV is coming from. So we have 135 minus 65, and it is giving us 60 mils. 70 mils. And this 70 mils, this basically tells you to say this amount of blood that is remaining in the ventricles after contraction has occurred. Okay, and the units, it is mils for this end diastolic and the end systolic, because we're just referring to the volume. And for the heart rate, we've mentioned about the heart rate. The normal, we did mention to that, is from 60 to 100. So anywhere between, can pick a number that is a normal one. So in our case with Madame Lumboka, we've been given the standard to be 18 beats per minute. Therefore, how do we calculate the cardiac output is equal to stroke volume times the heart rate. But I want us to hold on a minute on that one. We want to first of all to classify the different types of the stroke volumes that we have, the categories of the stroke volume that we have, before we come to that formula. So when you're dealing with the categories of the stroke volume, they are basically three. There's what you call as the preload, there's what we call as the contractility, and there's what we call as the afterload. So now let's begin with the preload. What exactly is the preload? So when you are referring to the preload, what you're just basically referring to is the degree of stretch of the myocardium to allow the ventricles to be filled with blood. So that degree of stretch of the myocardium to allow the ventricles to be filled with blood is what you're referring to as the preload. Okay, so now if you have the increase in the EDV, in the end diastolic blood pressure, in the end diastolic volume, that will cause an increase in the preload. So let me draw my let me get this, and okay, what do I want to get? What do I want to draw, guys? Oh, I want to show you how the preload occurs. Okay, so I've gotten my pen there. So assuming to say this is my ventricle, either right or left ventricle. So now during preload, we want this, I want blood to come into this ventricle and fill this ventricle. So now for this ventricle to be filled, we said the preload, this is just the degree of stretch of the myocardium. So the degree of stretch of the myocardium, we said inside here we are going to have during this preload, we are going to have our volume here, and this volume, it is what we call as the EDV, and we said the EDV, it is about 120 maybe to 140. Now the more that you are going to have this increase in the EDV, what do you think will happen to the to this chamber of the heart? You expect this chamber of the heart to do what? To stretch out, so that we can accommodate this EDV. So that basically tells you to say the increase in the EDV, the increase in the EDV will result into the increase in the ESV. I mean, increase in the preload. As simple as that. So that is what basically what we mean when you say the increase in the EDV will result into the increase in the ESV. Okay. There are some other things that we need to talk about that are going to result into the stroke volume being high, such as the respiratory pump, the vasomotor, the filling time, and so forth and so on. So, but those you can do those at your own time. So now we have gone into details by breaking down what is the cardiac output, which is equal to heart rate times the stroke volume. Just a quick summary: we've looked at the heart rate, the factors that contribute to the heart rate, and the factors that can result into a lower heart rate. We've looked at the stroke volume. So for the stroke volume, so we're not yet done. I've just mentioned one is being the preload. So contractility, this is just the activation of these myocardial muscles. So the contractility has to do much with the sympathetic nervous system that is going to cause these muscles, the smooth muscles, to do what? To contract. When these smooth muscles contract, so the higher the contractility, the higher the amount of blood that we're going to push out. So meaning to say, the higher the contractility, that will result into the higher the stroke volume. And the last point is the afterload. So the afterload is just basically